Hi everyone, I just wanted to redo this one because I think I messed it up a little bit in class. So just wanted to give you a proper rundown of how to do this sort of problem. Okay, so Ganymede is the largest of Jupiter's moons. It has a mass of 1.66 times 10 to the 23 kilograms and an orbital radius of 1.07 times 10 to the 6 kilometers and an orbital period of 6.18 times 10 to the 5 seconds, or 7.15 days. Use Kepler's third law to calculate the orbital radius in kilometers of Europa, another moon of Jupiter, which has an orbital period of 3.55 days. Okay, let me just start by saying in the book, when they show you this example, they keep the time in days. And you can do that because it's a ratio. I don't like that though. Personally, I think it's easy to mess up when you can keep things in non-SI units and when you can't keep them in SI units. I would rather you convert to SI units every time, because that way at least you know that you can do it that way. Okay, it might take an extra few seconds, but I think it's just going to, it'll avoid mistakes in the long run. If you are super confident with your maths and are happy to leave it in those non-SI units, go for it. But me personally, I think that you're much less likely to make a mistake if you change it to SI units. Okay, so we're using Kepler's third law, which is r cubed on t squared is some constant for everything orbiting a central point, okay, or a central mass. So in this case, our two moons are orbiting Jupiter, so r cubed on t squared will be a constant for both of them. All right, so if we work this out for Ganymede, what this constant is, so our constant is going to be, the radius of Ganymede is 1.07 times 10. Now, this is in kilometers. This is, again, one of those things you can leave if you're really confident. I would rather you not, so I'm going to change it to meters. 1.07 times 10 to the 9. So that's our radius. We need to cube that, divided by our period, which you could leave in days, but we're not going to. We're going to use in seconds, which is 6.18 times 10 to the 5. And we need to square that. Okay, so if we work out this, the value of our constant is 3.2 times 10 to the power of 15. Okay, that's our constant. Don't worry about units, they're not important. Okay, so if we know this constant, then we should be able to work out our data for Europa. So again, we know that r cubed on t squared is equal to that same constant because they're both orbiting the same thing, they're both orbiting Jupiter. So we want to find, what do we want? The orbital radius of Europa. Okay, we know the period. Well, actually, let's work out the period first. Let's get this exactly right. So the period is 3.55 multiplied by 24 hours in a day, multiplied by 60 minutes in an hour, multiplied by 60 seconds in a minute. Okay, and what will that give us? 3.55 times 24 times 60 times 60, which is 306,720 seconds. Oops, sorry, it's a bit messy. Okay, that's our period. So we know if we want to find r, we need to rearrange our equation a little bit. And so r cubed is going to be equal to t squared multiplied by our constant. And so r is going to be equal to the cubed root of t squared. Well, actually, let's put our numbers in. Cubed root of 306,720 squared multiplied by our constant, which we worked out above, 3.2 times 10 to the 15. All right, now a couple of notes on this. Firstly, if you're having difficulty with cubed roots on your calculator, just remember that a cubed root is exactly the same as multiplying something or raising something to the power of 1/3. Okay, so the square root of something is to the power of a half, so the cubed root of something is to the power of a third. So if you are having difficulty finding the cubed root button, or if you need to do larger powers, which you probably never need to, but just in case, you can just raise it to the power of a third. But if we calculate this, we get a radius of 6.71 multiplied by 10 to the 8 meters. Now, the question asks for it in kilometers, so we just divide by 1,000 and we get 6.71 times 10 to the 5 kilometers. Okay, so remember that cubed root, you can raise it to the power of a third to get it to do a cubed root. Okay, but the thing to remember here is just any two objects or any two satellites of a central mass, this r cubed on t squared is going to be a constant. Okay, for part B, use the orbital data for Ganymede to calculate the mass of Jupiter. All right, so this is probably the most elegant application of Kepler's third law. This is where Newton's proof of it really comes in handy. So we know from Newton's proof that r cubed on t squared is going to be equal to gm on 4 pi squared. Okay, so if we want to solve for m, which is the mass of Jupiter, which we do, we can rearrange this. I'm going to rearrange this slightly strangely, and you'll see why in a second. Our capital M is going to be equal to 4 pi squared multiplied by, I'm going to leave this in brackets, r cubed on t squared, divided by g. Now the reason I've done this is because we know already that value, r cubed on t squared, which is, that's the one we worked out before, 3.2 times 10 to the 15. Okay, so actually I might just put these proper numbers in. 6.67 times 10 to the negative 11. And then we know that r cubed on t squared, we can actually get rid of that because we know what it is. It is 3.2 times 10 to the 15. All right, again, put that into your calculator, work it out, and you should get a mass of Jupiter to be 1.9 times 10 to the 27 kilograms. Okay, and if you Google it, you'll find out, yeah, that is the correct mass of Jupiter. So this is how we can find out the mass of a central object given the radius and the period of any of its satellites, which is a beautiful application of physics. All right, last one. Calculate the orbital speed of Ganymede in kilometers per second. So what we can do here is use the equation we used. Well, this is similar to one of the ones we used before. It's not quite the same, but it's again related to those acceleration equations. In fact, any of them should work, but just use what we've got. So we are looking for v. V squared on r is going to be equal to 4 pi squared r on t squared. Okay, so this is just another one of those acceleration equations from one of the previous slides. Make sure you have all of those at your fingertips when you're going into the exam, because yeah, you might have any number of these variables, so it's good just to be able to find the right equation that you need. All right, so if we rearrange this, we will get v is equal to 4 pi squared r squared on t squared, square root of all of that. Well, lots of squares in there. Okay, so v, let's put in our data. V is equal to, well, I'll leave the square root to last, 4 pi squared multiplied by r. So the radius of Ganymede is 1.07 times 10 to the 9 meters. Remember, not kilometers. We want to square that, divided by the period squared. So 6.18 times 10 to the 5, all squared, and we want the square root of everything there. So if you put that into your calculator, you will get a velocity of 10,879 meters per second, which, you know, let's do it nicely. We'll make it into kilometers per second because that's what it asks us for. So let's just round it a little bit, 10.9 kilometers per second.